the ideal gas law, and the notes today are going to go pretty quick because I don't have graphs for you and I don't have examples for you, and I'm going to show you why, because a really freaky thing happens here with the ideal gas law. And it's so crazy to think that it actually works out this way. So let me get to our notes here, maybe. There we go. Okay. I want to show you something that we have tried to do long ago, and it's crazy how it worked out, that it actually worked out this way. We have done Boyle's law. I know, long, long ago. Boyle's law had P1 and V1 in it. Look at what I have up here in the numerator. I have my P1 and V1 going on right there, okay? That was Boyle's law, had P1 and V1 only in it. I guess I need my pen or it's going to keep moving to the next one. Then we had Avogadro's law. Avogadro's law had V1 and N1 in it. Been a while, you probably don't remember, but that's why it's going to be an open note test. So you don't have to memorize anything, you can just look it up. We did Charles' law. Charles' law had V1 and T1 in it. So scientists start looking at all these individual laws and they were like, I wonder if we can put them together. So they did. Here's what's totally freaky about this. When you put P1, V1, N1, and T1 together into this math, multiply the top and the bottom, then divide, you always end up with that number. Always. Whether I have a small balloon or a large balloon, whether it's in liquid nitrogen or at room temperature, regardless of the situation you have your gas at, if you measure and plug in your pressure and your volume and your moles and your temperature, it always gives you that number. Isn't that really weird that nature would work it out to always give the same number every single time? Well, it does. So this number we've given a special name to. Since it's always this number, it's a constant, we call that the ideal gas constant. Now, we don't want to keep saying ideal gas constant, especially in our equations. So what we do is we abbreviate it with the letter R. Why the letter R? Pretty much because all the other letters were already taken. I mean, like, I kid you not, that really, it doesn't like stand for anything in particular, but capital R was still available. Lowercase r is radius, but capital R was still available, so they used it for ideal gas constant. Now, what I said about it making always this number is true if, now catch my if I measure the volume in liters and the pressure in atmospheres and the moles in moles and the temperature in kelvins. But we don't always have to use those measurements. What if instead I measured in millimeters of mercury? Well, if instead of atmospheres I'm using millimeters of mercury, I would always get this number, 62.4, always. So depending on what I'm measuring, I get an actual different number, but it's just because I'm measuring in a different label, not because I'm doing any different math. So the difference between atmospheres and millimeters of mercury is what makes the number different. And I don't know if you caught on by now, but a torr is just a different name for a millimeter of mercury. Millimeters of mercury literally was Mr. Torricelli having a big tube of mercury with a meter stick against the side, and he measured every day whether the mercury was going up or down millimeters of mercury. Later, in his honor, because Torricelli did this process, taught us about atmospheric pressure and all that, they named the unit torr, short for Torricelli. So they are literally the same thing. That's why it's literally the same number. So we have two numbers it could possibly be. R could be measured in millimeters of mercury or torr and be 62.4. Or R could be measured in atmospheres and be 0.0821. Now there's one catch, notice. All three of these, the volume must be in liters. And we've already said all the temperatures need to be in kelvins for all the gas laws, but that is still true as well. So that is the ideal gas law. These numbers done with the math always make that. Now we don't normally write it this way though. So here's what I have in that little banner for you where I put the important formulas for each day. We normally write it this way. PV equals nRT. So pressure times volume equals moles times R times T, temperature. So that's our normal form. And here's our reminders, things that you probably know by now. But our pressure is going to be in atmospheres, millimeters of mercury, or torr. Volume must be in liters. Milliliters would not work. In Lab Wednesday, we're going to measure milliliters. One of the steps before you use this equation will be convert that to liters. If I need to say it, you're going to divide by 1,000 to make that happen. I'll remind you on lab day, you don't need to memorize that, but just know it has to be in liters. Moles is still going to be moles and temperature must still be in kelvins. So we've got our equation. We're going to do 4 examples. Now I want you to see this. Why only 4 when there's 5 letters in my equation? We always know what R is. So it means there's only 4 variables. P is a variable, V is a variable, N is a variable, and T is a variable. So that's what we got going on the back side. So go ahead and flip to the back of the page. We're going to do one of each kind of example, one for pressure, one for volume, one for moles, one for temperature, so you get the idea of what's going on here. And then we'll practice in Canvas. And that will be what we're up to today. Now, I know this from a friend's personal experience. It is not safe to put an aerosol canister in a campfire. Now, she wasn't putting it in a campfire. It was accidentally in her trash pile because she lived out in the country and was going to burn the trash because that's what you do when you live out in the country. You make a big pile of the trash and eventually a couple times a year, you just burn it all. There was an aerosol canister inside of it. And when it says, you know, they can explode, yes, they can. It exploded, shot flames at her. She ended up losing a bit of her ear to the flames. Now, all in all, not too bad, but it could have been a lot worse. So let's say we've got a 1 liter canister and it's holding 2.5 moles of gas. Like you think it's empty, but you know, they really never are fully empty. There's always some gas left inside. The temperature of the campfire is 1,400 degrees Celsius. That's not an unusual temperature for a fire. Fires can get really hot really fast. We are looking for the pressure. Now I'm going to make my little chart here. So I've got P, V, N, R, and T. And let's go to the numbers I circled. Which of those letters would liters have measured? Yeah, the volume, right? Liters is a good, let the labels tell you what that number is. Liters is a good way to measure volume. What about moles? Gives it away, right? What would I do with Celsius? Ah, yes, it's my temperature, right? But I can't leave it as Celsius. I have to turn it to kelvins. Do yourself a favor, do that right away so you don't forget. Just slap on a plus 273. And if I can do this in my head, I think I get 1673 kelvins. If I did that wrong, please let me know. Now I am asked what the pressure is, so there's my X, because I only have 4 variables, but I need to pick my R. So flip back to the front where I put the R's. I need an R that has liters and moles and kelvins in it, because that's what I'm seeing in my list here. Well, don't they all have liters and kelvins and moles in it? So which R do I pick? It doesn't matter. If I pick the one in liter atmospheres moles K, then my answer for pressure would be in atmospheres. If I pick the one for liters, millimeters of mercury mole K, then my answer would be in millimeters of mercury. Now here's the thing, please listen well. In Canvas, I tell you what is the pressure in, and I'll tell you whether I want millimeters of mercury or atmospheres, okay? So I'm gonna tell you what I want in Canvas. Here we get a pick. Let's go millimeters of mercury. I'm just picking one of the three. What's the number for R if I use millimeters of mercury? 62.5 right off the front. Again, I don't want you memorizing anything this unit. I want you able to look it up. That's why it's going to be an open notes test. Get to look that up. You're going to have your R there. Now that's liters, millimeters of mercury per mole per K. Did I write it incorrectly? 0.4. Okay. Thank you very much. That's supposed to be a 0.4 then. Appreciate it. Okay, let's do this. P V equals nRT. P is what I'm looking for. V is 1 liter. N is 2.5 moles. R is 62.4. I'm getting it right now. Thank you. Liters, millimeters of mercury, mole. Okay, it's a lot to squeeze in for the label, but I'm going to show you the importance of that in just a moment. 1,673 kelvins. And I need to solve all that. No big deal, actually. So I'm pausing a moment, letting you catch up. I'm going to show you what happens to the labels. Moles cancels moles. Kelvins cancels kelvins. Way over here, liters cancels liters. I have only one label left. What's that label that's left? Millimeters of mercury. So what's my pressure's label going to end up being? Millimeters of mercury. If I had used 0.0821 liter atmosphere mole Ks, atmospheres would be what's left, and then I'd be measuring it in atmospheres. That's how those labels work. That's why we have the 3 different numbers on the front. So to get the pressure, I'm going to take 2.5 times 62.4 millimeters of mercury times 1,673, all of that divided by 1.0. So if someone would help me out there, 2.5 times 62.4 times 1,673. What's the pressure in that can? It's probably a pretty big number. 260988, like that? Okay, that is a really big number. Now let's see. I've got 2 digits, 2 digits, 4 digits, lots of stuff going on. Normally I will tell you like round to the ones place or something. This is huge. Let's label it. This is 260,988 millimeters of mercury. It looks like I'd put a decimal in there. There should not be a decimal in there. Huge number. Keep in mind, normal air pressure is about 760. This is thousands of times more. That is exactly why aerosol canisters can go boom if they get into a fire. You don't want that. a bathroom where there's usually a bunch of like hairspray and air freshener and all that, that's a scary place to be in during a fire. Don't go hiding from a fire in your bathroom. Just get out of the house. Yeah. So there we go. That's our answer here. 260,988 millimeters of mercury. In Canvas, I'll tell you like round to the ones place or the tens place or wherever I want you to round. And in Canvas, I'll tell you, do I want millimeters of mercury or atmospheres? You can expect that, but it doesn't change the math we do. It's just multiplying some things and dividing by other things. Let's try another one. So if you look for number 2 in the top, this is the top right corner. If you were to take a volleyball scuba diving to a place where the pressure is 2,900 millimeters of mercury, and the temperature is 3 degrees Celsius, but the volleyball still has 0.21 moles of air in it, then what is the volume of the volleyball? So I'm going to make my little list. (2,900 millimeters of mercury is my pressure. I'm looking for the volume. I was told 0.0, there we go, 0.21 moles. We'll come back to R in just a moment, and the temperature is 3 degrees Celsius. Oh, let's not leave it in Celsius. We're going to add 273, which makes 276, if I can math. Now, when it comes to filling in R, this is super important. The only difference between the numbers we have for R is the label on the pressure. What is this pressure labeled in? Millimeters of mercury. So I need the number from the front that goes with millimeters of mercury. Well, we actually just used it. So 62.4, I believe, is what we used recently. Liters, millimeters of mercury, mole K. So use your R that matches the pressure. Only if you're looking for the pressure do you get a choice of R. You've got to make certain those pressure labels match. So PV equals nRT. So the volume's going to be N times R times T and divided by P. So I'm going to take 0.21 moles times 62.4 liters, millimeters of mercury, moles Kelvin, 276 kelvins. Also, the R will remind you to have your temperature in kelvins. It's a good reminder, so check those labels carefully. And let's see, I'm going to have on the bottom 2,900 millimeters of mercury. So that cancels that, that cancels that, that cancels that. Liters is what's left. Liters is a good label for volume. So I need someone to take 0.21 times 62.4 times 276 and take all of that after you multiply it and divide it by 2,900. I'm expecting the volume to be pretty small. What do we have? Say that again. 1.247. There we go. 1.247 liters. I don't know why I'm trying to write milliliters. Liters, 1.247 liters. I know it's got to be liters because up here, liters did not cancel out. That's why I know it's got to be liters there on my answer. Now I tell you in the bottom of that box what the normal here at atmospheric pressure level is for volleyball. So notice what has happened to the volleyball. By taking it down scuba diving, it's gotten a lot smaller. It is like a fifth of what it normally is. Lots smaller. Any questions about this example? Okay, 2 more and then we can get to practice. So let's go to the lower left corner. There we go. How many moles of gas are in a 30-liter scuba canister if the temperature of the canister is 298 Kelvin and the pressure is 204 atmospheres? And that's a pretty normal pressure for a scuba tank. And this is a pretty normal size for a scuba tank. So I've got 30 liters. I've got temperature. It's already in kelvins. That's helpful. And I've got 204 atmospheres. Make my little chart, PV, and R and T. Pressure, 204 atmospheres. Volume, 30 liters. Let the labels tell you what it is. I'm looking for moles, and the temperature is 298 kelvins. Now notice my pressures in atmospheres. So I need that number from the front that's in atmospheres. So flip it over to the front, find the number that is for atmospheres, 0.0821, I believe. Did I put enough zeros there? 1 0 between the decimal and the 8? Okay. Liters, atmospheres per mole per K. So if PV equals nRT, then N is going to equal PV divided by RT. So I'm going to take 204 atmospheres, multiply it by 30 liters, divide it by 0.0821 liter atmospheres, mole K, and times it by 298. Now the math here is a little interesting. Be very careful. Okay. Be very careful as you type this in. Atmospheres cancels atmospheres, liters cancels liters, kelvins cancels kelvins. 2 things to do. You have your choice, but you either multiply the top and write that number down, multiply the bottom, write that number down, and then divide. Or as you type it in the calculator, this is what I would do. As I type it in the calculator, I type in 204 times 30.0 divided by 0.0821 divided by 298. Since both numbers, 0.0821 and 298, are in the denominator, you want to divide by both. So if you're putting into your calculator all at once, be sure you hit 2 divide signs. A divide by and a divide by. Be careful about that. If you go 204 times 30 divided by 0.0821 times 298, it's going to divide only by the 0.0821 and take that whole answer and multiply it by 298, which is not what we want. So please type it in carefully. Okay, what do we get for our moles here? Having fits. There we go. 250 moles. Moles has not canceled. It's the label that did not cancel. So 250 moles there. I'm curious, did anyone else get 250? I see a yes and a yes and a no. Okay. So it's debatable. Again, it's going to come to typing it into your calculator carefully. And you do want to do that because you have to be sure you're dividing by both numbers on the bottom in the end. So you've got to do it one of those two ways I listed for you. And I can't even type this into my calculator for some reason. I don't know why my fat thumbs are stopping me. Let's try this again. Yeah, I'm going to go with 250. That's what I get. If you're not getting 250, I will gladly in a few minutes when we're done with the fourth example, walk through that with you. So please let me know if that's something you want to do. We absolutely can do that. All right, let's do the fourth and final example. And this is the process to make that liquid nitrogen we had fun with last time. To make liquid nitrogen, they took 5 moles of nitrogen in a 5-liter container and they pressurized it to 4,800 torr. Like that's a lot of pressure. 760 is regular pressure. So that's a lot of pressure, like 6 times pressure. PV and RT. I'm looking for the temperature of the nitrogen in the end. So I'm looking for that temperature. Pressure. Oh, I see a torr. That measures a good pressure. Let's do torr. Volume, I see liters. Let's use that as volume. Moles, I see moles. And then notice my pressure's in torr, so my R has to be the number with torr. 62.4 liters torr mole K. So again, open notes test, you've got the 3 numbers on the front of this page. Keep this page safe, and then you've always got your R to look up. I would never ask you to solve for R. We know what R is. I'm asking you for one of the other 4. PV will equal nRT, which actually means then to get T, I'm going to take P times V and divide it by N and R. So 4,800 torr times 5 liters divided by 5 moles and 62.4 liters torr mole K. Now watch the labels here. Torr is going to cancel torr, liters is going to cancel liters, moles is going to cancel moles. What's the label my temperature is going to be in? Yeah, the one that hasn't canceled is Kelvin. So my temperature is going to be in kelvins. I'm okay with that. I like kelvins. You don't have to put that into Celsius again for me. I'm not worried about that. I'll take kelvins. Kelvins is a fine way to tell me temperature. The math again, be careful with it. 4,800 times 5 divided by 5 divided by 62.4. If you like to do what I do, where I stick it all in the calculator at once, be certain you've got 1 multiply and 2 divide signs going on there. All right, be careful. What do we get for the temperature? It's going to be pretty small, I bet. 76.9, I like that. That's pretty small. 76.9 watts. Kelvins. Kelvins did not cancel. That's my label. Now that's a small amount of kelvins. That's cold. Take that number just for fun. Take that number, 76.9, and subtract 273. We get what? Negative. Okay, negative 196.1 degrees Celsius. Very negative Celsius. Very cold. Colder than even any place we've measured a temperature here on the Earth at. We've got close in Antarctica, but we've never quite reached that cold. So very, very cold. So kelvins are great. I'm okay with kelvins in Canvas as you practice. That's what I want. I just wanted to stress how low 76.9 kelvins really is. It's a very low number. Remember, normal is about 300 Kelvin. So that is a very low cold temperature. Okay, so that's the ideal gas law. Be careful you match your R to the label of your pressure. Pick the correct number. Be careful about that. There is practice in Canvas. It's got 8 questions. I'm pretty sure it's only 8. Where I'm going to ask you to find the pressure or the volume or the moles or the temperature. It will tell you where to round. I can help you figure out where that is if you'd like. I have no problem doing that. I can help you with any of the calculations. I can double check your work and type it in the calculator and see if we get the same thing. We have about an hour. We actually have an hour left in class here. Use this time well. Ask for help or ask me to check your work or look at what you did or whatever you'd like along the way. And then also let me point out, this is our 8th assignment in the unit. Today's assignment is number 8. I would strongly, strongly recommend before you